Okay, in the last lecture we have discussed about the implementation of FIR filter. So, in that we have used the unsigned multiplier called Brown multiplier, and then we have shown the simulation results. Okay. So, the next case study that I am going to take is IIR filter implementation, but this time I will use signed multiplier, because in most of the applications the data that we are going to handle can be negative also. Okay. So, a signed multiplier is very much useful in many applications. Okay. So, here I will take the implementation of IIR filter. So, in that a multiplier is involved. Okay. So, that multiplier I am going to implement by using a signed multiplier, which is called as Bauli multiplier. Okay. So, before going for the implementation of the IIR filter, first I will discuss about the signed multiplier. So, what is the mathematical background of this signed multiplier? Okay. This signed multiplier is not as straightforward as the unsigned multiplier. Here we have to develop some mathematical analysis to implement a signed multiplier. Okay. So, what is signed multiplier? So, we know that there are three ways to represent the signed numbers. Okay. So, first I will discuss about the signed number representation. So, in that we have signed magnitude, signed ones, complement, signed twos complement. So, if I want to explain this three number representations, if I take an example, suppose if I want to represent plus 12 and I want to store in 8-bit register. So, how to represent in signed magnitude? And how to represent in signed ones, complement, and signed throughs complement. So, what is the magnitude of this 12? 12 can be represented as 1100. Okay. So, this plus will be represented by, so in signed representation plus will be represented by 0, minus will be represented by 1, because the computer can understand only zeros and ones, it cannot understand plus and minus. So, we will represent this plus with 0 and minus with 1. So, in signed magnitude representation or signed ones or signed twos, so total I have 8 bits, because I am going to store in 8-bit register. Out of these 8 bits, so MSB bit is called as sign bit. There will be one sign bit, which is normally most significant bit, and there will be some magnitude bits, remaining 7 bits. So, this will be 7 bits. So, in general, if you want to represent in n bit register, 1 bit we have to use for sign, n minus 1 bits we have to use for magnitudes. So, sign bit is, because this is positive number, so 0. So, regardless of whether it is signed magnitude, signed ones or signed twos, the sign bit is always 0. Then coming for the magnitude, so what is the binary equivalent of 12 is 1100, but I want to store in 8-bit register, total 7 bits has to be there. So, I can append 3 zeros here. So, 1100. So, this is 000 1100. One important point here is, if the number is positive, all the three representations are same if number is positive. So, in signed ones also this is 0 0 0 1 1 0 0 only, in signed twos also 0 0 0 1 1 0 0 only. The only difference is in representing the negative numbers. Okay. So, if I take another example of say minus 12 and I want to store in same 8 bit register. So, if I take signed magnitude, signed ones, signed twos. So, there will be one sign bit and 7 magnitude bits. So, because this is negative number, negative minus 12, so sign bit is 1 in all the three representations. Okay. The magnitude bits will differ. Okay. So, what is this binary equivalent of 12 is 1100. Okay. So, in sign magnitude representation we will append 3 zeros because I want to store as a 7 bit magnitude. So, the magnitude bit remains 0 0 0 1 1 0 0. This is same as this except for the sign bit. Magnitude bits are same in sign magnitude representation if the number is positive or negative, the only sign bit will changes. Whereas, in case of signed ones complement representation, the sign bit anyhow will changes. In addition to this, magnitude bits will be the ones complement of this. So, the ones complement of this one is 0 becomes 1, 1 becomes 0. So, this is the representation of signed ones. 1 is sign bit followed by magnitude bits are 1 1 1 0 0 1 1. This is simply the ones complement of the magnitude of signed magnitude representation. And signed twos, sign bit is 1, the twos complement of this. So, ones complement is this, we have to add 1 to the ones complement. So, 1 1 1 0 0 1 1 plus 1. So, this is 1 plus 1 is 1 0, 1 plus 1 is 1 0 1 0 1 1 1. So, this is 1 1 1 0 1 0 0. So, in order to represent the negative numbers, we have three representations. In signed magnitude representation, sign bit is 1 and magnitude bits are simply the 7 bit equivalent in this case of 12. Okay. In signed ones complement representation, we have the sign bit as 1 and magnitude bits will be the ones complement of the magnitude bits of signed magnitude representation. And in signed twos complement representation, sign bit is 1 and the magnitude bits are the twos complement of the magnitude bits of the signed magnitude representation. So, out of these three, most commonly used representation is signed twos complement representation. So, why, what is the reason is, so if you add an array of numbers, okay, so if the final result is within the limits, we can neglect the intermediate overflows or underflows. Okay. That is the one of the beautiful feature of signed twos complement representation. That is the reason why this signed twos complement representation is more popular, and this will be used in many microprocessors and DSP processors. Okay. So, I will explain that property of the signed twos complement representation, which is the underflows or overflows can be neglected as long as the final result is within the limits. Okay. So, before going for this one, I will represent the signed twos complement representation, normalized signed twos complement representation. Fixed point. representation. We have floating point also, we are not discussing here the floating point representation. So, in floating point representation, we will be having exponent and mantissa. We need 2 register to store a single number, 1 register for storing the mantissa, 1 register to store the exponent. Okay. So, we are not going to that floating point representation, we will take the fixed point representation. So, if A is a W bit number, A is a W bit number, so in that A W minus 1 is the MSB bit, this will be acts as sign bit. So, in fixed point representation, after this sign bit there will be a binary point, this is binary point, then followed by W minus 1 magnitude bits. Okay. So, in the order of this weights, the next bit is A W minus 2, A W minus 3, so on up to we will get A 1 and A naught, A naught is LSB, and these W minus 1 bits are magnitude bits. So, you see the standard normalized signed 2's complement fixed point representation. Okay. If I use unsigned representation for W bit number, what is the range of the numbers that we can represent is 0 to 2 raised to the power of W minus 1. Okay. If it is 8 bit number, unsigned representation, what is the range? All 8 zeros, and the maximum number is all ones. This is in decimal, this is 0, this is 255. So, the range is 0 to 255. So, range will be normally represented by parenthesis, this is range 0 to 55. So, this is the range of the number that can be represented in unsigned format. So, in general this is in case of unsigned numbers, this is 0 to 2 raised to the power of W minus 1. Whereas, in case of signed numbers, this range will be minus 1, because here we are going to represent the negative numbers also. In unsigned there is no negative numbers, so the minimum bit is 0 only, whereas here the minimum bit is minus 1. And the maximum bit is 1 minus 2 raised to the power of minus of W minus 1. This I will show with an example, okay, how this will be this range. Suppose if I take W is equal to say 3 bit. So, if I take the positive number, I want to find out the maximum number will be positive number. So, for maximum number this is positive, so MSB bit is 0 point. So, in this representation MSB bit is 0 point. So, we will be having W minus 1 bits means 2 bits. So, for maximum value this 2 bits will be 1 1. Okay, because in positive numbers we are not going to take the 2's complement. So, this is the maximum possible 3 bit number in signed 2's complement representation. So, what is the decimal equivalent? How do you convert this? 0 into 2 raised to the power of 0 is the weight of this bit. This weight will be 2 raised to the power of minus 1, this weight will be 2 raised to the power of minus 2, plus 1 into 2 raised to the power of minus 1 plus 1 into 2 raised to the power of minus 2. So, this is equal to 1 by 2 plus 1 by 4. this is 4, 3 by 4. So, this can be represented as 1 minus 1 by 4, or in other words this is 1 minus 2 raised to the power of minus of 3 minus 1. Of course, 2, this is 2 can be written as 3 minus 1. So, I want to represent in this manner, so that I can explain the range of the numbers that can be represented. So, this is in the form of w is equal to 3. So, this is in the form of 1 minus 2 raised to the power of minus of w minus 1. This is the maximum positive number in case of w is equal to 3. If I take another example, say w is equal to 4, what is the maximum positive number? Is equal to 0 point, because positive number sign bit is 0, magnitude bit should be all ones, then only you will get maximum number. So, what is the decimal equivalent of this one? 0 into 2 raised to the power of 0 plus 2 raised to the power of minus 1 into 1, 2 raised to the power of minus 2, 2 raised to the power of minus 3. So, this is equal to 1 by 2 plus 1 by 4 plus 1 by 8. This can be written as 8, this is 4, 2, 7 by 8. This can be written as 1 minus 1 by 8, and again this is 1 minus of 2 raised to the power of minus of 4 minus 1. So, this is also in the form of this, w is 4. So, in place of w we have 4. So, in general the positive number can be a value which is 1 minus of 2 raised to the power of minus of w minus 1, where w is the number of bits in the given number. Okay. Then coming for the negative numbers, these are example for positive numbers. For negative numbers, if I take two examples again, if I take w is equal to 3, so what is the minimum possible negative number? Is sign bit is 1 followed by minimum is we should have all zeros, 2 zeros. So, what is the equivalent of this one? This is minus 1, because this is sign bit. So, the decimal equivalent, this is binary. So, decimal equivalent will be, so this will be minus 2 raised to the power of minus 1. Even here also you can call as minus, because this is minus bit, but anyhow 0 will becomes positive. This is minus 1, because this is sign bit is 1. So, this is 1 into 2 raised to the power of 0 plus 0 into 2 raised to the power of minus 1 plus 0 into 2 raised to the power of minus 2. So, understand this, why this minus sign is, because this value is negative. So, to get the negative value, if this bit is 1, you will get minus 1 as a result. If this bit is 0, anyhow minus also if you take, you will get 0 only, because the result is positive. So, this will be overall value is minus 1. If I take w is equal to 4, also same, the minimum negative number is 1.000, this is equivalent to minus 1. So, this is how the range of these numbers is limited, but the advantage of this one is we can neglect the intermediate overflows if the final result is within this range. Okay. So, this is actually binary representation of a w bit number in signed 2's complement fixed point representation of the w bit number. So, what is the corresponding decimal? What is the corresponding decimal equivalent of this one? We can see that here for negative numbers what you have taken minus sign. So, similarly I can take here also, this is minus AW minus 1 into 2 raised to the power of 0. We are going to use the same logic that we have used here in the examples. This is minus sign, okay. Plus what are these weights? AW minus 2, 2 raised to the power of minus 1 plus AW minus 3, 2 raised to the power of minus 2 plus so on up to A1 2 raised to the power of plus A0 2 raised to the power of. What are this? The exponents of this A1 and A0. We can see here that this W minus 3 means here 2, W minus 2 here means here 1. So, this is minus of. So, whatever the value here plus 1, okay, plus W minus 1. We are going to subtract W minus 1. So, here to get this minus 1, W minus 2 minus of W minus 1 is the value which is equal to W will get cancelled, will get minus 1. So, this minus 1 is the exponent of this. Similarly, here W minus 3 minus of W minus 1 will get minus 2. So, this minus 2. Now, we can tell here this one will be, if I assume that this is x, okay. So, 1 minus of x, 1 minus of x should be equal to, if I assume that this is x, this is W minus 2, this is 1. So, 1 minus of W minus 2 minus of W minus 1, sorry, this is 1 minus of W minus 1 will be the coefficient of this one. So, this will be equal to minus W. This minus 1 plus 1 get minus W minus plus 2. Okay. This is equal to minus of W minus 2. Is it clear? This is minus of W minus 2. And similarly, what about this? We will get minus of W minus 1, because the exponents are decreasing, minus 1 minus 2 if I consider the negative sign. So, minus 1 minus 2 so on up to minus of W minus 2, the last coefficient is minus of W minus 1. Okay. So, this is the decimal equivalent. So, we can alternatively use this binary representation as well as decimal representation to represent the negative numbers. So, this decimal representation can also be represented as, decimal representation can be simplified as, this is minus of A W minus 1, 2 raised to the power of 0 is 1 plus, I will make this as sigma, sigma j is equal to 1 to W minus 1 A W minus 1 minus j into 2 raised to the power of minus j. Is it satisfying this? So, this anyhow this is minus a suffix W minus 1 2 raised to the power of 0 is minus A W minus 1, this is okay. Now, for j is equal to 1 what happens? This becomes A W minus 2, A W minus 2 and coefficient is 2 raised to the power of minus 1. For j is equal to 2, W minus 3, 2 raised to the power of minus 2. For j is equal to W minus 1, the last one, this becomes W minus 1, W minus 1 get cancelled. So, A 0 and the coefficient is 2 raised to the power of minus of W minus 1. So, this is A in decimal form. This is one of the important representation that we are going to use in the remaining mathematical analysis of this signed 2's complement multiplier. Okay. So, this is some background, and coming for the property that as I have told, if I add a series of numbers, if the final result is within the range, we can neglect the intermediate overflows or underflows. So, that also I will explain with an example. This is property of 2's complement representation. If I take an example where there is overflow, okay, suppose if I take 3 minus 2. So, 3 how do you represent? So, in order to represent 3, how many bits are required? First of all, this is plus 3 minus 2. In fact, we can call as here all the numbers are, we have to represent the numbers along with the sign, plus 3 plus of minus 2, which is 3 minus 2. 3 is how many bits are required? The magnitude bit is 0 because positive number, and how many magnitude bits are required? 3 is nothing but 1 1, but in sin 2's complement representation, what will be this? This is 0 0 in sin 1's and 0 1 in sin 2's. So, the magnitude bit is 0 1, and minus 2 how do you represent? 1 dot, what is the binary equivalent of 2? Is 1 0 in sin magnitude representation, but we want sin 2's complement representation. So, this will be equivalent to 0 1 in sin 1's, and this will be 1 0 in sin 2's. So, this is 1 0. Of course, this 1 0 sin magnitude and sin 2's also same only for this particular example. This need not be same for all the numbers, right. Okay. So, if I want to perform this addition, 1 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, point, this one is 1. Okay. So, what should be the answer? In decimal it should be plus 1. Okay. But this is not the final answer. So, final answer can be obtained by taking the 2's complement of this one, because we are representing in 2's complement. 2's complement of this one is final answer. Okay. So, what is the 2's complement of this? So, 1's complement is 0 0, for 1 1, 1's complement is 0 0, 2's complement will be 0 1, and for this 0. This is 1 1 1 is 0 0 0 plus 1 is 0 0 1. This is 0.01. So, this will represent positive number, and this one is magnitude. Magnitude, this is equal to 1. So, this is plus 1. So, this is plus 1. So, you see how we can perform this sin 2's complement addition. There is no subtraction at all here, because we are going to represent the number along with the sign. Okay. So, in order to study that property, intermediate overflows and all, if I take the second example, if I want to add 2 plus 2 minus 3. Okay. So, how do you represent? This is nothing but plus 2 plus 2 plus minus 3. So, how do you represent plus 2? Plus is sign bit is 0, magnitude bits is 1 0, because for positive numbers all the 3 representations are same. Okay. If you want to explain this with the help of examples, okay, I will initially take example of plus 3 plus of minus 2. This is nothing but actually 3 minus 2. Okay. But normally in 2's complement we will take along with the sign. Okay. So, what is the result? Expected result is plus 1. Okay. So, if you want to explain this in sin 2's complement, how this addition will be performed, plus 3, how many bits are required to represent plus 3? So, this is equal to plus represent the sign bit is 0 and the magnitude bits are 3. How many bits are required to represent 3? Is 1 1, okay, in binary equivalent. But in case of positive numbers, this is sign magnitude or signed 1s or signed 2s, all the 3 representations are same. Okay. So, this is 0.11 minus 2, this is equal to sign bit is 1 and what is the signed magnitude representation of the 2 is 10 is signed magnitude representation, but because this is negative number we have 3 different representations. So, this is 0 1 in signed ones and this is we have to add 1 to this one. So, 0 1 plus 1 is 1 plus 0 is 1 0 1. So, 1 0 signed 2s, because here we are going to perform this using signed 2s complement representation. So, we have to take signed 2s complement representation which is 1 0. Then this only addition only, because I have taken along with these signs. So, the subtraction becomes addition. Okay. This is 1, 1 plus 1 is 1 0, 1 plus 1 is 1 0. So, this overflows you can neglect, because so how many bits you have taken? 3 bits, this is 3 bit representation. So, what is the range of the numbers that can be represented in 3 bit? The range is for w is equal to 3 is minus 1 is the negative number, that is the minimum number, positive number is 1 minus of 2 raised to the power of minus of w minus 1. So, this is nothing but for w is equal to 3, 3 minus 2 becomes 2. So, this is 1 by 4. So, this is equal to minus 1 2 plus what is the value? 1 minus of 2 raised to the power of minus of 3 minus 1, which is equal to 1 minus 1 by 4, 3 by 4, this is plus 3 by 4. So, what is the result of this 3 minus 2? In fact, is plus 1. Okay. We can neglect this carry. So, remaining what is the magnitude? This represents place. In positive numbers we have directly take the magnitude. What is the magnitude equivalent of this one? Is 1. So, result is plus 1, this is plus 1. Okay. So, if I take the second example, if I want to perform 2 plus 2 minus 3. So, you see nothing but plus 2 plus 2 plus minus 3. So, what is plus 2? Is sign bit is 0, magnitude bit is 1 0, because positive number magnitude, signed 1, signed 2 is same. Another plus 2 is 0 point again 1 0. First I will perform addition of these two numbers. So, 0 1 0 0.1. So, what is the magnitude of this one? This represent minus sign, this is minus. So, minus, what is the magnitude? 2's complement of this. What is the 2's complement of this one? Is, so 0 0 is 1 1 plus 1 is 1 0 1 0, this is 4. But this is not valid result. We know that this should be plus 1. So, within the range. Okay. So, within the range of this 3 bit representation. Okay. So, even though if you have the intermediate overflow or underflow, this is called underflow, we can neglect this. You neglect this intermediate result and you proceed with the final this thing, you take minus 3 also. So, minus 3 is sign bit is 1, magnitude bits are for minus 3. So, this is 1 1 is signed 1's representation, signed magnitude representation, signed 1's is 0 0, signed 2's is 0 1. So, 0 1. If I add this one 1 0, 1 plus 1 is 1 0, 1 you neglect. So, this represent positive and this represent plus 1. So, this is the final result is correct. In between we have got some invalid result, but the final result is correct. So, it is the one of the important feature of the sin 2's complement representation. Even though if you get some underflows or overflows in between, as long as the final result is within the range, so we can neglect the intermediate overflows and underflows. This is the reason why the sin 2's complement representation is more popular. Okay. Now, coming back for this signed multiplier, how to perform the multiplication. Let A is equal to A3 dot A2 A1 A0. This is signed 2's complement fixed point representation. A3 is the sign bit, A2 A1 A0 are magnitude bits, and B is another 4 bit number. We are discussing about the 4 bit by 4 bit sin 2's complement multiplication. Okay. B3 dot B2 B1 B0. This is in binary form. Okay. So, I have to perform multiplication as y is equal to AB. Okay. Of course, if you multiply two 4 bit numbers, result can be 16 bit, but here I am going to truncate the lower order 8 bits and I will store only the 4 bits of the result only. If you want, you can retain the remaining bits also, but it will increase the complexity. So, there is a compromise here again between the complexity and the accuracy. Okay. Here I am restricting this result to 4 bit only. So, this will be something like y3 is sign bit, y2, y1, y0 are magnitude bits. Okay. So, how to perform this multiplication? So, in order to perform this multiplication, if I write this in the decimal form, this is binary representation. If I take in decimal form, so what is A is minus A3, this we have already discussed, plus A2 2 raised to the power of minus 1 plus A1 2 raised to the power of minus 2 plus A0 2 raised to the power of minus 3. B is minus B3 sign bit plus B2 2 raised to the power of minus 1 plus B1 2 raised to the power of minus 2 plus B0 2 raised to the power of minus 3. Okay. So, if you want to perform AB, I will fix one number and I will then I will represent the other number in the decimal form, and I will use a rule called Horner's rule. Okay. So, y is equal to A I will fix as it is, B I will represent this number minus B3 plus B2 2 raised to the power of minus 1 plus B1 2 raised to the power of minus 2 plus B0 2 raised to the power of minus 3. So, this is nothing but minus A B3 plus, in fact, A B2 2 raised to the power of minus 1 plus A B1 2 raised to the power of minus 2 plus A B0 2 raised to the power of minus 3. This I am going to write cleverly, so that the complexity of the multiplication architecture will become less complex. I will write this as A B2 plus, I will write again A B1 plus A B0 2 raised to the power of minus 1, then 2 raised to the power of minus 1, then 2 raised to the power of minus 1. We just check whether these two expressions are same or not. Minus AB3 is as it is. AB2 will be 2 raised to the power of minus 1. This AB2, this overall this bracket and this bracket. So, this will multiply, this AB2 will multiply with only this 2 raised to the power of minus 1. And what about AB1? This will multiply 2 times, this with this as well as this. So, that this becomes AB1 becomes 2 raised to the power of minus 2. And what about AB0? This will multiply 3 times, this one 2 raised to the power of minus 1, another 2 raised to the power of minus 1, another 2 raised to the power of minus 1. So, these two are same. This particular representation is called the representation using Harna's rule. This is very much useful representation to get a low complexity architecture for signed multiplier. Okay. Now, here we have minus AB3, AB2 and all. Okay. So, A is this one. What is minus A? If A is this, implies what is minus A. If I know minus A, then B3 you have to multiply with each coefficient with B3. Okay. So, in signed 2's complement representation, given A, how to obtain minus A? Minus A is nothing but 2's complement. Okay. So, minus A can be obtained using the 2's complement. So, A is in binary form, this is A3 dot A2 A1 A0. Minus A becomes the 1's complement is A3 bar, A2 bar, A1 bar, A0 bar plus 1. 1 has to be added at the least significant bit. This is equal to minus A. If want in decimal form, this is binary representation. In decimal form, minus A is nothing but this is minus A3 bar plus A2 bar 2 raised to the power of minus 1 plus A1 bar 2 raised to the power of minus 2 plus A0 bar 2 raised to the power of minus 3 plus this extra term will come plus 2 raised to the power of minus 3. Okay. So, this is the complete representation of minus A in both binary form as well as decimal form. So, these results we are going to use to obtain the final architecture. This is one important thing. So, another thing is given A, we require A into 2 raised to the power of minus 1 also. This is A into 2 raised to the power of minus 1. So, given A, how to obtain A raised to the power of A into 2 raised to the power of minus 1. What is A 2 raised to the power of minus 1? Okay. So, this is equal to what is A in decimal form? Minus A3 plus A2 2 raised to the power of minus 1 plus A1 2 raised to the power of minus 2 plus A0 2 raised to the power of minus 3 into 2 raised to the power of minus 1. This is equal to minus A3 2 raised to the power of minus 1 plus A2 2 raised to the power of minus 2. This minus 1 is there, another minus 1 minus 2 plus A1 2 raised to the power of minus 3 plus A0 2 raised to the power of minus 4. But I want to store this A into 2 raised to the power of minus 1 in 4-bit register only. This is A, I have stored in 4-bit register. How do you store this A in 4-bit register? A3 is the MSB bit followed by dot A2, A1, A0. So, what is the weights of this one? The weight of this one is 2 raised to the power of 0, weight of this one is 2 raised to the power of minus 1, weight of this is 2 raised to the power of minus 2, weight of this is 2 raised to the power of minus 3. But I want to store A into 2 raised to the power of minus 1 also in the 4-bit register. So, what is expected? Here there will be sign bit followed by 3 bits with weights of 2 raised to the power of minus 1, minus 2, minus 3. So, there is no question of minus 4. Okay. So, that is why if I write this in equivalent form, I will write this as minus A3 plus A3 2 raised to the power of minus 1. So, this single term I am going to write equivalent to this. We can easily verify that this minus A3 2 raised to the power of minus 1 is equivalent to minus A3 plus A3 2 raised to the power of minus 1. Okay. Because if I take minus A3 plus A2 2 raised to the power of minus A3 2 raised to the power of minus 1, if I take A3 as common, this is equal to minus 1 plus 1 by 2. Okay. So, this is nothing but minus 2 plus 1 1 by 2. So, this is minus 2, this is minus 1 plus half is minus half, this is minus A3 by 2, that is equal to minus A3 2 raised to the power of minus 1. This one. So, minus A3 2 raised to the power of minus 1 can be written as minus A3 plus A raised to the power of A3 into 2 raised to the power of minus 1, plus the remaining terms are A2 2 raised to the power of minus 2 plus A1 2 raised to the power of minus 3 plus A0 2 raised to the power of minus 4. But I want to store in 4-bit register this A into 2 raised to the power of minus 1 value also. So, this value will be left, this will be lost, because I do not have that position. The positions are only 2 raised to the power of minus 1 position, minus 2 position, minus 3. Minus 4 position is not there in 4-bit register. So, this will be lost. So, then what will be stored? The MSB minus sign. So, A is with minus sign, the A3, here also minus A3 is there, A3 dot 2 raised to the power of minus 1 term. What is the 2 raised to the power of minus 1 term? Here we have minus A3, so the first bit is A3, and then 2 raised to the power of minus 1 term is A2, so A2, 2 raised to the power of minus 2 term is A1, so A1, 2 raised to the power of minus 3 term is A0, A0. Here what is 2 raised to the power of minus 1 is A3 only, minus 2 is A2, minus 1 is A1, and A0 is lost. So, this is one of the important result. If I have A as A3 dot A2, A1, A0, then A into 2 raised to the power of minus 1 will be having A3, A3, A2, A1, and A0 will be lost. This is what is called the important property, which is called sign extension property. So, the sign 2's complement representation will be having sign extension property. So, given A as A3 dot A2, A1, A0, A into 2 raised to the power of minus 1 becomes A3 dot A3, A2, A1, A0 will be lost. In a similar manner, you can easily derive that if I want A into 2 raised to the power of minus 2 in 4-bit register, so the sign bit will be A3 itself, but it will be copied twice, A2 and A1, A0 will be lost. And if I want to write A into 2 raised to the power of minus 3, then all A3s, A2, A1, A0 will be lost. So, this is equal to A3 dot A3 dot A3 dot A3. Okay. So, this is another important result. Using these results, we are going to derive the architecture for 4-bit by 4-bit signed multiplier. Now, coming for this algorithm. So, what is value of y we have obtained is minus AB3 plus AB2 plus AB1 plus AB0 2 raised to the power of minus 1 whole into 2 raised to the power of minus 1 whole into 2 raised to the power of minus 1. This is what is the Horner's rule. Okay. So, now if I take the multiplication of A3 dot A2 A1 A0 into B3 dot B2 B1 B0. So, first I will develop the algorithm using this Horner's rule, then I will map this algorithm onto the architecture. Here I am going to develop algorithm. Later I will map this algorithm onto the architecture. So, the first thing is we will start with the A B0 2 raised to the power of minus 1. So, what is A B0? A B0 is nothing but A B0 is nothing but A is A minus A3 plus A2 2 raised to the power of minus 1 plus a1 2 raised to the power of minus 2 plus a0 2 raised to the power of minus 3 into b0. So, this is nothing but minus a3 b0 plus a2 b0 2 raised to the power of minus 1 plus a1 b0 2 raised to the power of minus 2 plus a0 b0 2 raised to the power of minus 3. So, what is a b0 is simply we have to multiply with each and every bit. Okay. So, this is a3 b0 dot a2 b0 because this is a2 b0 after dot which is 2 raised to the power of minus 1 term, and a3 b0 is 2 raised to the power of 0 term, and 2 raised to the power of minus 2 term is a1 b0, 2 raised to the power of minus 3 term is a0 b0. So, this will represent a b0, this a b0 in this total term. Suppose if I want a b0 into 2 raised to the power of minus 1 also. So, in the previous we have shown that if a is this, what is a into 2 raised to the power of minus 1 is simply a3 a2, the sign bit will be copied. So, if I want this one, this will be lost to get a b0 2 raised to the power of minus 1, this bit will be copied a3 b0, this is sign extension. So, this will be, if you remove this a0 b0 term and if I keep this a3 b0, a3 b0, a2 b0, a1 b0, this will be a b0 2 raised to the power of minus 1, this entire thing. Then what you have to do? You have to add this to a b1. So, a b0 means a3 b0, a2 b0, a1 b0, a0 b0. If I want a b1 means, so a3 b1, a2 b1, a1 b1, a0 b1. So, this plus, because I want to perform up to here now, a b1 is nothing but, so a0 b, this is a3 b0 is there, and this is last one is a0 b0, but now we want a b1. So, in place of b0 we have b1, this b0 b1, this b0 b1, this b0 b1. So, this is a0 b1, a1 b1, a2 b1, a3 b1. So, if I add this, I will call this partial products, this is not the final product. So, I will call as this is partial product 1 and this is 0th bit, partial product 1, this is 1th bit, partial product 1, this is 2nd bit, partial product 1, this is 3rd bit. This is the notation that I am following. So, what will be this value now? This complete value is a b1 plus a b0 2 raised to the power of minus 1. This is the total value we have obtained, this is total this. This we have to again shift. So, this if we want to shift with 2 raised to the power of minus 1, then we have to neglect this, then you copy this sign bit p3 1. So, this will be now into 2 raised to the power of minus 1 up to here. Then for that we have to add a b2. So, a b2 is nothing but again, so a0 b2, a1 b2, a2 b2, a3 b2. So, if I perform this, I will get another partial product which we will call as pp2 second partial product 0th bit, pp2 1 bit, pp3 second bit, pp2 second bit, pp2 third bit. So, this result is total result is this a b1 plus a b0 2 raised to the power of minus 1, this into 2 raised to the power of minus 1 plus a b2 up to here. This entire thing is again we have to shift with 2 raised to the power of minus 1, finally we have to add this. So, this if you want to shift by this entire thing, if you want to shift by 2 raised to the power of minus 1, then you neglect this and you extend the sign of this PP32. Then finally, you have to add minus A3. We know minus A3 is, if I know A as this one, minus A is this. So, minus A3, A2, A1, A0 plus you will get one extra term called 2 raised to the power of minus 3. So, what will be minus AB3 is A3, A0 bar B3, A1 bar B3, A2 bar B3, A3 bar B3, because 2's complement. Then we will get one B3 here, because there is 2 raised to the power of minus 3 for minus A. If you multiply with minus A with B3, then all the terms minus A3 bar B3, A2 bar B3, A1 bar B3, A0 bar B3, and then finally simply B3, because here only one. So, this is this B3. Finally, you will get this result. You are calling as this is Y3 dot Y2, Y1, Y0. This is the final result. This is the algorithm. So, how to map this algorithm onto the architecture we will discuss in the next lecture. Thank you.